Hi everybody. So this second video here we're going to do Kirchhoff's current law. We're going to go through and analyze and we're going to use some of the values that we've already come up with in our previous video and how we broke it down into kind of equivalent circuits as we went through. We're going to need those values as we progress to use Kirchhoff's current law. So the very first thing I need to know is I need to know what my total current actually is. And this comes from a given voltage of 120 volts divided by my 240 ohms. And I get 0.5 amps or 500 milliamps. Okay, so that means Kirchhoff's current law was the whole sum of the currents entering a junction have to equal the sum of the currents leaving the junction, or if you took all of those currents together and added them, they would have to equal zero, depending on how you want to analyze that. But really, I like to think what's leaving the source has to be what's coming back to the source. So that means the current here, that's my I total, that's half an amp. And the current here has to be half an amp. So we're just going to leave this with current. I'm not even going to do a single voltage calculation for this, but you can see how it would be nice and easy to calculate the voltage drop across that 200 ohm component. But really the difficult part of this is trying to analyze. I've got current traveling in 3 different directions now. And there's a couple of different ways that I can do this. But what I'm trying to figure out is the current entering this junction has to equal all 3 of these currents leaving this junction. And we know that, based on Ohm's law, that the current is inversely proportional with its opposition. So the lower the opposition, the higher the current. The higher the opposition, the lower the current. Okay, so what we're going to go back is, if you remember, and if you hopefully you still have these values with you, we created an equivalent circuit. When we try and figure out what is going in all 3 directions and doing that in one step is it's possible. It's just a little bit complex. So let's simplify it for us. And what we're going to do is I want to go back to where we calculated what the equivalent circuit was for these. So we added the 180 inversely with the 120, come up with an equivalent for that, and then added it with the 18 ohms. And what we ended up with was an equivalent circuit that looked like this. Okay? Now I have current only traveling in 2 directions. This makes it a little bit simpler for us. So I have current, my half an amp, coming into this junction, and I only have current traveling in 2 different directions. This greatly simplifies it for us. And so this equivalent, I'm going to write that as R equivalent, REQ, was 90 ohms. This is still the same R3, it's 70 ohms. So I'm going to use the principle of Kirchhoff when he said that the amount of current that's going to be going through there is inversely proportional with the opposition. Sorry, that was Ohm's law saying that, not Kirchhoff. Ohm's law says that. So what I want to do is I want to come up with a way to analyze, well, what percentage of current is going to flow to this 90 ohm equivalent, and what equivalent, sorry, that should say 72. Okay, so I want to know the percentage, and it's inversely proportional with the current. So that doesn't mean just flip the value. over because you're going to get them a little bit mixed up. But what I can do is I can take my equivalent circuit, and when I add these together, the R1, 2, 3, and 4, what I came up with an equivalent circuit of these two in parallel was 40 ohms. Okay, so when if I did R equivalent inversely with R3, oh, that's a B, this equaled 40 ohms. So I know now that if I take and do 90 ohms inversely with 40 ohms, I'm going to get the percentage of the opposition for that one component. And what that is going to tell me is the percentage of the current that actually is going to flow in that direction. So this ends up being 0.444, a whole bunch of decimals repeating. So, or 44% of the current is going to flow, 44.444% is going to flow in that direction. Okay? So now all I have to do is take my 0.444 or 44% and multiply it by my current to know how much current is actually going to flow in that direction. So 44% or 0.444 times 0.5 amps is 0.222 whole bunch of or amps or 222.222 bunch of, it's all repeating milliamps. Well, this actually gives us a huge advantage because I can do the same thing with this 72. I can say 72 ohms divided by 40 ohms. And remember, it's inversely proportional because it's our current principle. And I get what's left over, which is 0.555 or 55.5% of the current will travel down. Okay. So I get, when I do this, I say 0.55 times 0.5 amps is equal to 0.277 repeating, or 277.777 milliamps. So now I actually know, leaving this junction, going in this direction, that current is 0.277 amps. I know the current going up is that 222, but what you'll notice is that now I can go back. So I know that this current is 0.277 amps. So it's going to flow all the way through this circuit. It's going to come back up here, and it is going to be 0.277 amps entering into that junction. Well, the beautiful thing about this is that when these two currents divide, or they split and then enter back into this junction here, my current here has to be what's left over. Because the current entering this junction has to equal back up to my 0.5 amps. So the only thing I have left now is how to solve for current right here. So how do I solve for current flowing to the 120 and the 180? Well, if you remember, we came up with an equivalent circuit for that as well. So the R equivalent for this was 72 ohms. So now I can use that same percentage calculation that I did in the past. Okay, I can do 180 ohms divided by 72 ohms inversely, and this is going to give me a percentage. So it's 40%. And 40% of this 0.222 amps. So I'm going to fire a bunch of those decimals into my calculator. So it kind of resembles. So I get 0.088 repeating amps, or 88.88 milliamps. Now what you can do is you can just subtract that from 0.22222, or if we want to keep, so we just have, we get a little bit more practice with that inverse function. You could do 120 divided by 72 ohms, all to the inverse. And that will give me a percentage. So 120 divided by 72 is 60%, because if you remember, this was 0.4 or 40%. So this one has to be 0.6, because those, or 60%, because that has to equal back to 100% of that 222 milliamps. So we take our 0.66, multiply that by our milliamps, our 0.2, and we get 0.133, or 133.33 milliamps. So this traveling to the 120 is 0.133 amps. Traveling up, I'm going to erase that because I'm going to make it in the same color as their current arrow, 0.133 amps. And this was 0.8, sorry, missed the decimal, 0.088 amps. So we might be off by a couple of decimal points, way down to, depending on how many you actually kept. But now, the thing that I like about this is now it's nice and simple. I have all of the currents and the oppositions. I can go calculate all the voltage drops. One thing that you could do, if you would like to simplify this a little bit further, rather than doing the inverse, it is possible. I like to keep it as the inverse. It reminds me that it's inversely proportional with current. So the higher the opposition, the lower the current. The lower the opposition, the higher current. And this proves it. So I have 180 ohms and 88 milliamps. I have 120 ohms and 133 milliamps. So I have more current flowing through the resistor with the lower opposition, which is exactly how that should go. But you can do these inverse. You could just leave this as 72 over 180, and this will end up with 0.4. So you don't have to do the inverse. You can literally invert that right from the beginning. For me, it's a process thing and how I identify with it. Just to keep things simple. But it is, oh, you know what? I drew that way above the screen. You're not going to have any idea what I just wrote there. Okay, so this, sorry, you could have left as 72 over 180. That is the inverse of, I did it again, 72 over 180. That's the inverse of 180 over 72. Same thing. But again, I do that for myself. It's a way to remember, why did I write it in that fashion? So this is Kirchhoff's current law. It's just using current and the percentage of the opposition traveling in each direction to figure out what the current is leaving each junction. So I hope this has helped. This is a good one to get kicked off with, because that junction right at the beginning of that circuit where current's traveling in 3 different directions makes us really, really think. And we have to use those equivalent models that we built from calculate total resistance. So I hope this has helped. Next couple of videos we're going to talk about how to do this with voltage. And how I can use Kirchhoff's voltage law to do something similar with this.